implicit differentiation, all right? We've been doing differentiation, but if you think about it, every time we take the derivative, we get y on one side by itself and then take the derivative, right? So y is isolated on one side. It is not inside the function, it's on the outside of the function. So that's what we refer to as explicit differentiation, when I have y by itself on one side and I can take the derivative of what's on the other side. But if I come across something like x squared plus y squared is equal to 25, if I'm going to take the derivative as we've been doing it, I would first have to solve for y. So I would have to go through and get y by itself on one side in order to be able to take that derivative explicitly. So if I did that, I would subtract the x squared over to the other side, so I'd have y squared is 25 minus x squared. And then I'd take the square root of both sides, so I'd have y is equal to plus or minus the square root of 25 minus x squared. Once I had y alone on one side, then I'd be able to take the derivative. So let's think about how we would take that derivative. I would start by rewriting that radical with an exponent. So I would write it to the 1/2 so that I could use power rule, and going to have to use chain rule as well, right? So we could go through and say if I have a quantity to the 1/2, that would be 1/2 that quantity to the negative 1/2 times the derivative of that quantity. So the derivative of the 25 minus x squared would be negative 2x. Then I could do the 1/2 times negative 2, and that would leave me with negative x in the top. And then I had that 25 minus x squared to the negative 1/2, so I can move it down to the denominator and put it under the radical. And that would be my derivative, all right? I also then could evaluate that at a particular point. Like if they said find the derivative at the point 3, 4, because y could be either a positive or a negative square root of 25 minus x squared, when they asked me to find it at the point 3, 4, since y is positive, then I'm using the positive piece out of those two. And so I would plug in the point 3, 4, so put 3 in for x and put 3 in for x. So 3 in for x, 3 in for x. I would get a slope or a derivative at that point of negative 3/4. All right? I can do that exact same thing using something called implicit differentiation. In implicit differentiation, I don't have to get y on the outside. I can leave y where it is in the function and take my derivative. Because look at my next scenario. The next one they're going to ask me to do in example number 2, we have x to the third plus y to the third is equal to 6xy. How are you even going to get y by itself? Like, okay, I'll move this guy over here and move the x cubed over here, and I can't like factor out a y. I mean, I'm going to have to do all kinds of craziness to try to get y by itself, and then what I'm going to be left with would be an equation that would be so obnoxious to try to take the derivative of, it's just not going to be practical. So implicit differentiation in some cases, might be an easier alternative. In other cases, it might be the only alternative. All right? So let's go back and let's take that same equation that we just worked explicitly, and let's see how we could do it implicitly. In implicit differentiation, I'm going to go through and take the derivative of both sides of the equation with respect to x. Now, what we mean by that is typically when we take the derivative, like dy dx, we're taking the derivative of y with respect to x, or the derivative of y in terms of x. That's what was happening right here. When we went through and we did the derivative of y, and y was written entirely in terms of x. So I'm going to go through and take the derivative of y of my function with respect to x, or in terms of x. The problem is, if I take the derivative of x squared, no problem. The derivative of x squared, that's in terms of x, so the derivative of x squared, I can just say is 2x. But when I get to the derivative of y squared, that's not in terms of x. How am I supposed to take the derivative of y squared if it's in terms of y instead of in terms of x? Well, I'm going to treat it like I would chain rule. I'm going to go through and I'm going to say this is y to the second. So if I were to take the derivative of y to the second, that would be 2y to the first. and I'm going to think of y as my inside function and say, okay, what's the derivative of y? And since I don't know, I'm going to leave a dy dx in there. Well, how come I didn't have to do that with the x? Well, I am actually doing that with the x. When I take the derivative of x squared, I'm saying 2x to the 1 times the derivative of x, but the derivative of x is just 1. So I get 2x to the 1 times 1, and I just get 2x. So when I take the derivative in terms of x, I don't have to do anything differently. But when I take the derivative in terms of y, because that is not with respect to x, it's the derivative of y in terms of x. Since it is not in terms of x, it's in terms of y, I'm going to do it with chain rule, where I'm going to say, think of y as a quantity. So if I have a quantity to the second power, that would be 2 times that quantity to the first power, and then we would multiply by the derivative of that quantity. I don't know what the derivative of y is, so I just leave dy dx in there because I don't know what it is. I can't replace it with anything. So that's the reasoning behind what we're doing here. Let's make it practical. When you take the derivative, if what you're taking the derivative of is in terms of x, just do it like you've always done it. Do it like normal. If you take the derivative of something in terms of y, take the derivative like you normally would, and then put in a dy dx with it. Okay? So if we're being practical here, anytime you take the derivative of y, take the derivative just like you always would, but you're going to have to leave a dy dx with it. Because I don't know what the derivative of y is in terms of x. I can't replace it. I got to leave it in there. Okay? So the derivative of 25 will be 0. So we've done step number 1 where we've taken the derivative of both sides of the equation with respect to x. If we took the derivative of y, we left the dy dx in there. Step number 2, I got to get dy dx on one side by itself. I mean, that's my goal, right? What is the derivative? Dy dx is the derivative, so get dy dx on one side by itself so we can say the derivative equals this, right? So if I'm going to get dy dx on one side by itself, then I'm going to subtract this 2x over to the other side. And then to get dy dx by itself, I'm going to need to divide both sides by 2y. Do any simplification that I can. So those 2's would cancel each other out, and we'll get negative x over y. And we look at that and go, that's not the same answer that we got. I thought we said if we took the derivative implicitly or we took the derivative explicitly, we would get the same thing. We actually did. When we took the derivative over here, this derivative is in terms of x only, right? When we took the derivative x implicitly, because we don't have to get rid of y or get y by itself, this derivative is going to have x and y in it. But if I'll go back and say, okay, my derivative is negative x over y, what was y equal to? Well, y was equal to the square root of 25 minus x squared. If I put the square root of 25 minus x squared right there, that is the exact same thing. So I did get the same answer. It's just that this derivative is in terms of x only, and this derivative is in terms of x and y. So if I want to see that they're the same, all I would need to do is just take this derivative and replace y with what it's equal to, and then they will be identical. It's really easy to see when I plug in a point, because when I plug in a point, all the x's and the y's go away, and I just get a value, right? So remember that we had evaluated this derivative at the point 3, 4. Let's come over here then and let's do this derivative at the point 3, 4. I would put 3 in for x, and I would put 4 in for y, and I'd get the same thing. I'd get the negative 3/4, the same thing that we had gotten over here, right? Okay. All right, look at example 2. Example 2 was the one that we said we don't even want to attempt to try and get y by itself and do that one explicitly, right? There are some times that I won't even be able to get y by itself and take the and then take the derivative explicitly. So let's do this one implicitly. So we're going to start off with the derivative of x cubed. And remember that we're taking the derivative of both sides of the equation with respect to x. That means we'll take the derivative just like we normally do, but if we hit a y, we're going to take the derivative like normal and leave a dy dx with it, okay? So when I take the derivative of x cubed, no problem. That's in terms of x, so I take its derivative like normal, 3x squared. Then I get to the derivative of y cubed. That's not in terms of x, so I'm going to take the derivative like I normally do. The derivative of y cubed would be 3y squared, and then since it was in terms of y, I just leave a dy dx in there with it. All right, then let's go to the other side. On the other side, we have 6 times x times y. So I have a product. I'm going to put the 6 with the x. I could put it with the x or the y, but I'm going to put it with the x. So I'm going to think of 6x as one term, and I'm going to think of y as one term. And so I'm going to do my product. So I'm going to do first times derivative of the second plus second times the derivative of the first. So first times derivative of second plus second times derivative of first. All right, so the derivative of y would just be 1, and because it's in terms of y, I have to leave a dy dx in there, right? So I'd have 1 dy dx. And then plus second times derivative of first. The first term was 6x, so the derivative of 6x is just 6. All right, then step number 2, we want to solve for dy dx. We want to get dy dx on one side by itself. And sometimes that's pretty obvious, like it was in this first one up here. Sometimes that's a little more involved of a process, so I gave you a few steps that might help you with that as well, all right? The first thing I want to do is get all of my dy dx terms on one side and everything else on the other side, all right? So like this guy right here has dy dx in it, so I'll leave it on the left. This guy right here has dy dx in it, so I'm going to subtract it over to the left. This guy did not have dy dx in it. I'm going to get him out of my way. I'm going to subtract him over to the right. So this guy got subtracted over here. This one stayed where it was. This one got subtracted over to the left. This one stayed where it was. So all the dy dx terms on the left-hand side, everything else on the right-hand side. All right, then we want to factor out dy dx. Just like you would a common factor. You could throw a z on top of it if you wanted to. If you had 3y squared z minus 6xz, if you took the z out, you would be left with just the 3y squared minus 6x, right? Same idea. If I take out the dy dx, I would be left with the 3y squared minus 6x. Here's an easy way to do that as well. If you literally put your finger over this dy dx and put your finger over this dy dx, the only thing that would be left is the 3y squared minus 6x. So put your finger over all of your dy dx's, and what you can see left over is your other factor. So we'll take out the dy dx, and we're left with 3y squared minus 6x. And now to get dy dx by itself, then we could just divide both sides by that other factor, right? So let's divide both sides by that 3y squared minus 6x. We always want to give our answer in lowest terms. So if there would be anything that I could factor and cancel, I'd want to do that. And I can take out a greatest common factor of 3 in the numerator and a greatest common factor of 3 in the denominator and cancel those out. And then what remains is my derivative. So for example 2, they asked me to first find the derivative, and then they said find the tangent to the equation at the point 3,3. All right, so basically we could go through then and say, okay, we found the derivative, now let's find the derivative at the point 3,3. So I'm going to put 3 in for x and 3 in for y. So 3 in for y, 3 in for x, 3 in for y, 3 in for x. And the derivative at the point 3,3 would be negative 1. They also asked me for example number 2 to tell the points on the curve where we have a horizontal tangent line. Now, we've talked about horizontal tangent lines before. Our horizontal tangent line is just wherever our derivative is equal to 0. So if I look at, this is the equation for my derivative, so if I think about where that derivative equals 0, the only place a fraction equals 0 is where its numerator equals 0, right? So we want to go through and we want to set that numerator, 2y minus x squared, we want to set that equal to 0. The only problem is it has two unknowns, an x and a y. I can't solve for x and y at the same time, right? So if you're trying to solve for two unknowns, you need two equations, like a system of two equations with two unknowns, right? The only other equation I have is my original equation. So that's what I can use. I can say, okay, here's my numerator that was set equal to 0. That's my first equation. And then here's the original equation that we had to work with. That's our second equation. Now I have a system of two equations with two unknowns, and I can solve. I'm going to solve by substitution. Remember, for substitution, you solve one of the equations for one of the unknowns and then plug it into the other equation, right? This definitely looked like the easier equation to me. And so I solved it for y. I didn't want to solve for x because of the radical. So I solved it for y. So solve one of the equations for one of the unknowns and then plug that into the other equation, right? So if y is equal to 1/2 x squared, then in my original equation, I'm going to replace each of the y's with 1/2 x squared. All right, so if I simplify, 1/2 cubed is 1/8, and x squared cubed is x to the 6th. And then over here, 6 times 1/2 is 3, and x times x squared is x cubed. Now let's move it all over to one side. So I'm going to subtract this x cubed, so that would leave me 2x cubed. And I'm going to subtract the 1/8 x to the 6th. Take out my greatest common factor. So they have an x to the 3rd in common, so I'll take out that x cubed. And that would leave me with my other factor of 2 minus 1/8 x cubed. And let's set each of those factors equal to 0. So if I go through and I set x cubed equal to 0, I'll get x is equal to 0 as a triple root. Up here, if I set 2 minus 1/8 x cubed equal to 0, I'm going to add that 1/8 x cubed to the other side, multiply both sides by 8, and then take the cube root of both sides. So you could write it as the cube root of 16, or you could write it as 16 to the 1/3, or you could give the decimal for it. So if they just wanted to know what's the x value where you have a horizontal tangent line, there it is. They asked me for the points where I had a horizontal tangent line. So those are the x values. I'm just going to plug back in to find the y values. I could plug back into either equation. I'm definitely plugging back into the easier one, right? So that easier equation was y is equal to 1/2 x squared. So I'll plug 0 back in, and I'll plug the 16 to the 1/3 back in. And so that would give us our 2 points. And again, if you don't like it written this way, another way that you could write that, down here,